Hello everyone, welcome back to another video. I hope you're having a good day wherever you may be. In today's video we will be talking about series and parallel combinations of resistors. And so to get started we'll go ahead and talk about series resistors. So what that means, I'll draw a quick example here. So we have resistor 1 and resistor 2 connected. I'll call resistor 1 R1 and resistor 2 R2. So a series combination is when two things are connected in a node together here. So let me go ahead and do this color. And so we could easily combine them into one resistor, which we can call the equivalent resistance, which we will label Req. So we can make this equation called Req is equal to R1 plus R2. Now this can apply to as many resistors as we want, so it doesn't have to be just the two. So for example, we could have R1, R2, R3, R4, R5 for example. I'll go ahead and label those. So our equivalent resistance here would simply just be all of them added together. Okay, so this is series. Let me write that real quick. Now parallel, I will write that. Give you a quick example here. So this is when we have resistors in a combination looking like this. Okay, so here we can label R1 and R2. So our equivalent resistance in the circuit will end up looking like this once we are done. So we must combine these two in this fashion. And there's a different equation for parallel resistors. So we will have the equivalent resistance is equal to R1 times R2 over R1 plus R2. Or another equation that we can use, which gives us the exact same result, can be Req is equal to 1 over R1 plus 1 over R2 to the exponent of -1. So the same principle applies as series resistors, to where we can have as many resistors as we want. So for example, we can say let me draw this out here, sorry. And just to save a little bit of time, we'll only do 3 resistors. R3, R2, R1. So we can't really use the first equation that we had up here, for example, for this parallel combination of resistors, because there's 3. And we need to do different algebraic manipulation of the equation. But we can still apply this equation right here. So essentially, we will just have Req is equal to 1 over R1 plus 1 over R2 plus 1 over R3 to the power -1. And if we were to type that in our calculator, that would give us the right answer. And if you start with this equation right here, you could algebraically manipulate that to give you an equation that would sort of look like this one, but I find it easier to just use this one right here and plug in your calculator, because it will give you the answer. So now I will go ahead and do a couple examples here of how to actually simplify these equations, or these circuits I should say. So I'll go ahead and do this example here. So we'll do give me 1 second. Okay. We'll have R1. We'll say this is R3, and then R2, R4. And I will give each resistor values on the side here, so we'll say R1 is equal to 1.8 ohms. R2, we will also say is equal to 1.8 ohms. R3, let's also make 1.8 ohms. Then R4, we'll change that up a little bit. Let's say 4.7 ohms. Okay, so now we can identify what is in series first. So I'll go ahead and write that, our series combinations of resistors. I'll go ahead and highlight those. So we have R1 and R3. That is our first series combination of resistors, and our second ones are R2 and R4. Okay, so now I'll write this in red. So now we can say R13, because we're combining resistors R1 and R3 in series, is equal to R1 plus R3. And I got this equation here from above, from this example, where we said the equivalent resistance, or REQ, is equal to the resistors in series, which is R1 and R2 in this example above. And here we said R1 plus R3, so we have R1, 3, and R1, 3, by the way, is the equivalent resistance. So that would be 1.8 plus 1.8 is equal to 3.6 ohms. Okay, and same thing for R2 and R4, so we can have the equivalent resistance, which is R24, is equal to R2 plus R4, which is equal to 1.8 plus, then we have 4.7. And then adding those two together, we get 6.5 ohms. And by the way, these numbers I got here for R1, R2, R3, and R4 just came from the side here. These are the given values already for the circuit. And so since we have made these into series combinations, now we can redraw this circuit as just a parallel combination of resistors. Okay, so now we can say R13 and R24. And we can get the values for these two from above here, which we calculated. So R13 was 3.6 ohms, and R24 is equal to 6.5 ohms. And now we can combine these two in parallel. Okay, so now we can use the equation that we have above from this example. We can use this first equation right here, or we could use the second equation that I have circled. It doesn't matter, they'll both give you the same answer. For simplicity, we'll go ahead and stick with the first equation that I mentioned. So we'll have REQ is equal to R13 times R24 over R13 plus R24. Okay, so if we write this out with numbers, we will get 3.6 times 6.5 over 3.6 plus 6.5, which will give us 23.4 over 10.1, which gives us a final result of 2.32 ohms. And that will be our equivalent resistance of the circuit. Now, doing it with the other equation to show you that we get the same result here, let me go ahead and do that. So REQ is equal to 1 over R13 plus 1 over R24 to the power negative 1. So we just can plug in our numbers here that we had for R13 and R24. So we have 1 over 3.6 plus 1 over 6.5 to the power negative 1. And as we can see, we will get the same answer of 2.32 ohms. Now, when it comes to parallel combinations of resistors and using these equations, it's really up to preference. Personally, I prefer the second equation here that is circled in blue, but there are some people that prefer the first equation, and both work just fine. Just use the one that you feel most comfortable with. And when it comes to series and parallel combinations of resistors, it is easiest to just get a lot of practice. The more you look at these circuits, the more that you try to manipulate the resistors in series and parallel combinations, you will become an expert at it. And this final result, our equivalent resistance, has the circuit with just one resistor, which we can say Req. So once again, boxed in blue, this is our result of what that would look like in actual circuit form. And the reason why this is important is because whenever we're doing circuit analysis in future videos using KCL and KVL, for example, it's easiest to find the equivalent resistance and deal with circuit analysis that way instead of having to deal with multiple numbers and values. So I think that will be it for this video. I'm very thankful for the time that you took to watch this video, and I hope you have a good day.